Of stuff in this section is stuff from physics last year, so we don't have to go into a ton of detail, but when we get to structures, when we get to trusses, the theories of forces and moments are going to be used, okay? So you've learned about forces last year, Newton's laws, F equals ma, all that great stuff. You also learned about torque last year, torque being the product of force times the lever arm. So when you turn a wrench, you apply a force, and the length of the wrench was the lever arm from last year. And a torque is related to a moment. Okay, we'll talk about this in this section, how moments come about. But moments are desires of structures to rotate or not rotate. For example, on the third floor, extending from the school, is the flagpole, right? You've seen it before? Yeah. It's supported with a little truss structure underneath it, actually. It's got a little support there. And the actual flagpole, the old one actually, the new one doesn't have this. I wonder how the new one works better. But the old one used to have little half moons cut into the flag. Did you ever see that? Yeah. Does the new one have it? It does. Okay, I wasn't sure. Why does it have to have it, Caroline? Exactly. It would be like a sail, and it would snap. It would not. But it would maybe snap out of the building, right? So the structure itself has a moment about a rotation axis. So the rotation axis would be where it's connected to the actual building, and it wants to rotate because of the wind, but it's not going to do that because of those holes in the actual flag. It's also supported in the building. It's usually things that extend from a structure are cantilevered. A cantilevered structure is something like this. Imagine, okay.
Like the thing you said in Grand Canyon, where it hangs off.
Yeah, the glass bridge on the Grand Canyon you're talking about? That glass bridge extends over, but there's no support in the middle of it. It's the actual structure. So something that's cantilevered, to give you a quick, actually I'll just draw it to make it easier. I was going to demo it, but it's hard to demonstrate that. Imagine this is a building right here. Whoops. Here's your building. Something that is not cantilevered could be attached maybe with a pin or some sort of a, you call it a node. It could be attached with, a pin is the right word for it, but not an actual pin, but a cylindrical pin, like a long rod. It could be attached there and extend from the building, but something that's cantilevered actually is in the building itself. Part of the structure is embedded in the building. So this is fixed into the building. Like imagine you remove 2 bricks out of the side of a brick house, and you took a steel beam and slid it into the building, and then finished over the bricks and then solidified it and closed off what it was, and the beam was in the building, and it was being supported inside the building by maybe a clamp or something that was holding it there. That's cantilevered. So something that's cantilevered can resist a lot more moment or torque than something that has a pin fix. A pin is easily rotating. It's usually actually free to rotate when there's a pin. You can lock a pin in several directions, which will cause it not to rotate, but generally something that's cantilevered has more strength in rotation. All right, let's go right into it. So first, we talked about forces last year. They are simply a cause of acceleration. A cause of acceleration. Now, what happens if 2 forces are acting in opposite directions and they balance each other? What are you in a state of? What's the term for that? Good memory. Equilibrium. Okay, when there's equilibrium, there's no acceleration because there's no net force. And we talked already about contact forces. And specifically, when it comes to engineering, the forces that we care about for structures, because I'm really applying this to structures right now, is gravity and any contact force. Contact forces can be variable. So, believe it or not, the wind is a contact force because the wind contacts the actual material. Friction between 2 different bodies that actually cause it to not move or to move. Either one, friction can help you or hurt you. And then gravity. Gravity usually is the load of the actual element itself pulling down. Like the actual element has weight. So when that flagpole extends from the building, the weight of the flagpole and the flag is always pulling down on the building, or always pulling down on the pole. So as a result, there's always a force acting on it. So if we were to draw that, here's what it would look like. And the weight you would draw from the center. Okay, just like we did in class for physics, we always make sure to draw our weight right from the center of the object, showing that the weight acts down. Now, if the wind is pushing against this object, it can cause it to turn or pull, or maybe torque a little bit, that's where moments can come into play. Let's see. Some examples we just mentioned real quick: weight, normal force, and friction. Normal force is a reactive force. It's always perpendicular to the surface. We talked about that last year. What keeps an object on the surface? The normal force pushes back up. Without the normal force pushing back up, this object would fall through the surface. Buildings also have normal forces. So the actual building itself is supported by the ground. You have the foundation of the building, and that's what's supporting the building itself. Let's see. Friction we talked about already last year. We talked about the concept of friction, that the friction force can be something that usually resists motion, right? It stops something from sliding and moving along the surface. But friction with structures could also help a building. For example, if you think about buildings that are earthquake ready, what's the word for it? Yeah, earthquake ready, like they're prone to a lot of earthquakes in that area. They use mass spring damper systems inside to absorb a lot of the shock. Well, friction is involved there. There's a lot of friction that actually absorbs that energy. Yeah.
Have you ever seen those videos of like really tall buildings during earthquakes that like sway and
Yeah, they have to. That's the whole idea.
yeah, but it's like
Scary.
there's videos where it's like really noticeable in the office and like it feels like the building's about to like take
There's
over.
like buildings in Manhattan that do that because they're so tall, just like big.
Think about it, right? Remember what's torque? Torque is force times the lever arm. As you get higher, as the building gets taller, the force of the wind, besides the wind being stronger, the force applies more torque because it's further from the rotation axis, which is the ground.
Like that, the new apartment building that they said like rose down, like you can feel it from the top.
I hate that the roof
You
is
feel it shaking? Yeah, I mean, like think about it, guys. Look, if the wind is pushing here, it doesn't have much of an effect. But if it's pushing here, this is the lever arm, the length of the building, or the height. So the taller the building, the more moment from wind occurs, or the more torque on the building. So it's going to sway naturally. Now, the ones with earthquakes, remind me of my laptop I did. Before we end here tomorrow, I'll show you a quick simulation of that. The one with earthquakes, buildings are meant to sway because if they didn't, what would happen?
It was not.
It would snap and crumble, right? So if something was not flexible at all and it was going to occur or was going to undergo an earthquake, it would break. That's why brick is not actually good when it comes to structures. Brick, we used to think when we were younger, when you learn, right, when you're literally riding it, you got the head, you got the sticks, and then you got the bricks. It's a terrible example, though.
That's
Really?
Three Little Pigs, not Red Riding.
Oh, it's Three Little Pigs?
Yeah. Red Riding Hood's the one with the grandma.
That's right, the wall feeds them. But the idea is that if the bricks are all lined up and they have some sort of a maybe rebar or like a fibrous material going through them, that could actually absorb some of the shock, but the bricks themselves will still crumble. So you see combinations of that, especially in like any third world countries where they're building like houses and small huts. They'll use things like straw or things that have like some sort of tension in them, and they'll mix them in with the clay, or is the word adobe, right? The material they used to build like houses and stuff in other countries, and they'll mix that in with it so that the actual structure is not only like a solid, but it has these like what we would call rebar. If you ever looked at concrete and there's metal running through concrete, it prevents the concrete from snapping, from breaking under tension. Concrete is very strong under pressure, but it can break.
But I stopped using iron, like when to make skyscrapers, they couldn't make skyscrapers out of iron because it's really brittle.
Interesting. I didn't even know that. Iron is very brittle.
That's why they went to
So they went to steel because steel has more ductility.
Yeah.
Because I think about it like tall enough.
Yeah, that's why in like old New York you don't have skyscrapers because they made a lot of the buildings of iron.
Good fun fact. I didn't know that. Just let Miss Custer probably talking about
Have
it.
you
They
seen
probably
that?
did. I don't know why.
Have you seen the YouTube channel where the guy like lives in like the woods in Australia and he like makes like he started out like with the Bronze Age and the Stone Age and he makes like huts out of clay.
Oh, the primitive
and
thing,
shut-
like
primitive
Yeah.
technology.
Oh, yeah.
He doesn't talk about it.
Oh my God, it's
great.
so cool.
Because he doesn't start off with this. Hey guys, today we're back with another
No,
video.
yeah, it's just like there's
He
no.
goes right into it. It's
so refreshing.
Definitely. That sounds awesome. That's interesting. And he goes through all the different ages and talks about how the materials have changed. And everything. How do you know that?
Well,
Because
he shows you what
he
he
does
does.
a very good job of showing what
Really?
he's doing. Yeah.
And he doesn't talk.
He doesn't talk.
Like he made bow and arrows.
That's so
without
cool.
from scratch.
Are you showing me?
And he
Yeah,
released
he
it.
scratches.
Hey, what's up, guys?
It's really cool.
Oh,
Like he makes a
He made like a
forge thing,
whole
like, and
village.
it's just like it's really
That's cool.
awesome.
It's like
I gotta look at
Minecraft.
Time.
It's called primitive technology.
Primitive technology. All right, next thing I want to talk about, so we're going to use this to analyze truss structures, is free body diagrams, and we mentioned these last year. Remember, a free body diagram talks about the forces acting on an object, So when we look at truss structures a little bit later, we're going to see that each of these nodes, the nodes are where the actual members meet. So this is a very simple truss structure. Okay, imagine there's water under here, and that's a bridge. You see these all over the place, right? Truss structures are everywhere. It's beautiful. So every one of these nodes, or where the members meet, can be analyzed with a free body diagram. And what you can do actually is determine the amount of force in each member as a result to see if that member would either break in tension or in compression. So we're going to use those ideas throughout the chapter, so we have to remember free body diagrams and how they work. So if I push on a desk like this, you can show a force acting on the object. The weight pulls down, the normal force pushes up, maybe friction pushes back. So recall from last year in physics, free body diagrams.
Would, like, in that case, wouldn't all the nodes be symmetrical?
They wouldn't. You mean like would the forces acting on all of them be?
Yeah, that's what
Some are different. Like this has 2 members coming from it. This
No.
has 1, 2, 3, 4.
But I mean, like, so the 2 bottom nodes,
Yeah.
those would be the same.
But here's the thing. You're assuming everything's symmetrical. What if a car is only here? And it's not, right? Yeah. So under a dead load, meaning like just the bridge alone, absolutely. But as soon as and it's never a dead load on bridges. Even without cars on them, the wind is different in different locations. So each member acts differently. But yeah, symmetrically wise, you're going to see this year without any applied load, or if applied load is right down the middle, there's definitely perfect symmetry. Or if it's just symmetrically out the same. We talked about forces acting at an angle. We need to remember this. Okay, remember last year when something was at an angle, we had to think about the x and y component. X was cosine, y was sine. X was cosine, y was sine. It's the easy way to remember it, if you remember from physics. So I'm talking about this. Imagine here's the node itself, and that force is applied. And that force is applied at an angle of, let's say, 20 degrees. And it's a 50 Newton force. By the way, I'm going to finally go to pound forces this year because, really in the US, we're going to use pound forces. You don't actually use newtons. In physics, I use newtons because it's a standard international unit that everybody uses. But if you're ever going to consider doing anything in engineering, you're not going to be talking about newtons. In the US, at least you're not. So if this were the case, we need to consider the fact that anything pulled or pushed or at an angle can be broken into perpendicular components. It's very important to look at perpendicular components because we can sum the forces in the y and sum the forces in the x. When it's at an angle, we can't do much with that. So remember, this is how it looks. This is the x projection. And this is the y projection. Remember, it's simply like you're making a triangle out of it. And if you can't see where the triangle is, I'll show you in a sec. Oops, cosine 20, right?
How convenient. This is the problem. That's what I'm doing right now.
Yeah, I know, right? So the triangle you can see is right here. There's the right triangle. If I put that dashed line in. So that's a triangle, okay? The y direction of force is really the height of the triangle. The x direction of the force is the base of the triangle. The hypotenuse is the actual force. So if you forget that this is where this should be sine, not cosine. Jeez. I got so used to writing it. Relax. So the length of these vectors are always going to be less than the hypotenuse, because the hypotenuse is the longest vector of the triangle. So fx and fy are always going to be a smaller value. And you guys know this, I hope, from last year. Cosine and sine of an angle. The cosine of an angle and the sine of an angle is always going to be a decimal. Do you remember that from math last year? Or a fraction of decimal? Like, cosine of 30, 0.866, sine of 30, 1/2. Did you memorize these special angles last year? Yeah, remember the unit circle? It was like radical 3/2. Yeah, radical 3/2, 0.866. So these are always going to be fractions. So a fraction times 50 is going to be something less than 50.
I don't think that's a 20-degree angle.
All right, Connie, really? Anyway, let's take a look at a quick example. All right, and this is what we're going to be doing with truss structure. So I want to go through one example together at least. So if you're going to analyze and see if this node itself is in a state of equilibrium, we can take a look at all the forces and align them in the x and y directions. So some of them already are in the x and y directions. Which of them are in the x direction only? Which of these forces, and assume you see it. Which is only in the x? Yeah, right here. This is only in the x, right? The other forces are all in the y direction. Now, what do we need? What else do we need in order to determine if it's in equilibrium? Yeah, we got good. So we have some negative forces to balance the positive, very good. But geometrically, what did I not give you? You need angles. You need the angles, right? So I purposely didn't. I want you to give me an idea of what you think these angles would be reasonably. So give me an idea. What do you think this angle could be? About 45, because this is 90 here. So you could say it's about half of that. So let's drop that, or let's put this one as 45. Now, I also need to do this, remember. I need to draw myself a horizontal. And the angle that I'm going to use is always between the horizontal and the vector. And whenever we did forces last year, the angle was always given between the vector itself and the horizontal. The vector and the horizontal. The vector and the horizontal. So we need to fill in those other three angles still. So the one below, I'm going to put 55, just because I think it's a little bit bigger than the one above. Again, I'm estimating. If I had a protractor, I would just simply measure it. I mean, I do have a protractor I can measure, I guess.
So you're not doing them all from the same point? Doing this over?
No, it's not like, yeah, it's a great question. It's not from the what is that called? Math.
I forget.
Yeah, there's a word for it. Like the starting side, you know what I'm talking about?
I think it's called the starting side.
No, it's not, that's a fancy word for it.
Alright.
You're not starting from the 250 line at all, no. You're not going around from there.
Horizon.
No, there's another word in there. It's killing me, whatever. On this side, let's say this is around 30 degrees, and let's say this last one is 25 degrees. So if that's the case, all we need to do is break up these forces into x and y components. How many times do we have to do it? All right? 4 times. One time we don't have to. 250 is only pulling to the right. It's only in the x. The other 4 forces, though, those need to be broken into components. So, in the x direction, we start. We've got 250 acting to the right. We've got the 200, and that's going to the right and down.
The initial side and the terminal.
Thank you. Initial side. That's all it is. Initial side. Oh, brain fart. So this 200-pound force right here is acting down and to the right. Again, if you don't understand that, look up. Down and to the right. That's the way it acts. So since it acts to the right, I put a positive. I don't put 200. That's not the whole force. I have to use the cosine now of the angle. Okay, that will always give me the x component. The x component. The 300-pound force up here is acting up and to the right. So it's still positive because it's still to the right. And the angle is now 45. The other two forces, the other two, x-wise, we can see that they're pulling back. So this is to the left and up. This one is to the left and down. So we know since they're to the left, what do we put? Yeah, minus here. And that's what it looks like in the x direction. We'd have to sum all those values together and see what we get as an overall force. But that's only in the x direction. We have to do the same thing in the y direction. The 250-pound force does not matter in the y direction because it's only acting in the x. So we don't have to include this one for the y direction because it's only pulling to the right. But these are all pulling either up or down, up or down. So the ones pulling up are going to be 300 pounds, and that's now sine 45. Plus 310, sine 30. So I've taken into account already these two that are pulling up, and I've used the sine of these angles, and I put positives because they're pulling up. The ones that are pulling down, I'm going to put, instead of positives, negatives. I don't know what those numbers will be. You can check. What would they need to be for you to be in a state of equilibrium? What would the answers all have to be? 0. You gotta get 0 in equilibrium. If it's balanced vertically and if it's balanced horizontally, you know that automatically that it's in a state of equilibrium because there's no net force. If there's a positive in the y direction, it means that the overall force is pushing up. If there's a negative in the x, the overall force is pushing to the left. So you can see whether this node, it's usually a pin at a joint, a pin. The pin itself is under stress at all times. The goal is that it's not under stress at all times. Now, the other part we're going to talk about, we're going to see this with structures a little bit, is shear stress and how shear stress works also. And shear stress is like, imagine here's a pin, and there's a plate coming off the pin this way, and another plate attached this way, and they're pulling against each other. It could cause the bolts to snap. See what I'm saying? They're not both pulling from the same location, so they equal and opposite of each other. Even if these forces are equal and opposite, if this one is pulling here, and this force is pulling here, they're both under shear stress, or they're both causing shear stress. So the bolt itself, it could snap like this. Sorry, Miss Myers, I should have put. Sorry about that. You can take all of them back if you want. No. My bad.
Shear stress.
So shear stress would cause something to actually snap, like in the perpendicular direction to his axis. So this is a bolt or a pin, it would snap this way.
You really
Okay? It would not snap that way, it would not snap this. I'm not gonna break the pencil. But yeah, you could do this with a well, what's something that would work? Yeah, toothpick, a dowel rod. If you pull hard enough this way, it would snap under shear stress. If you bend it, it would snap under tension very easily. I'm trying to think. Yeah, you probably wouldn't. A bolt usually would take a lot of force for it to shear. But if you remember, one of those catastrophes I talked about in the beginning of the year, you remember the one at the second floor of the hotel fell? We went over catastrophes, major catastrophes earlier in the year. It was the Hyatt Hotel or the Reeves or one of these hotels where the second floor collapsed and fell on people. It had to do with the bolts that were supposed to be running up and down. It was supposed to be one solid bolt and it was two pieces and it ended up snapping in the middle. That was under shear stress, that makes sense.
Damn.
In SpongeBob, they put a pole on the top floor, and then it just collapsed on itself.
Because they put what on the top floor?
A
Pool. Pool. It probably didn't snap under, or probably didn't fell under shear stress there, though, right?
It eliminated the hotel that they built. So.
It was a historical representation of
Clearly, with SpongeBob, right? So a moment I talked about real quick again, but a moment is something that causes a torque. A torque. Okay, it's a force acting at a distance. A force acting at a distance. That's all a moment is going to be. So we talk about this term next called fixed end moments. Fixed end moments. So these are the reaction moments when a structure is fixed. So for example, let's say we've got a cliff with a canyon in between. You've got a bridge that extends from one end to the other, like this. Well, at the ends, they're not just going into the actual cliff. It's embedded into the rock, and it's fixed there. But as you walk across it, or as objects are brought across this bridge, what's going to happen naturally to the bridge? Even though you don't see it really, what does it do? It bends, like on a microscopic level, it's got to bend. You apply force on a structure, even if it bends 1 times 10 to the negative 35th meters, meaning like 0.01 meters, it will bend a little bit. Okay? What?
That many zeros?
The idea here is that at the ends, you have what are called reaction moments. So if this pulls down, the end of it wants to react to cause it not to bend that way, so it's a moment that you would draw like this. And on this end, it would look like that. So these are called reaction moments, and the idea is that this bridge wants to pull down, the actual cantilever beam rotates back and pulls back against it in this direction. It's like an anti-torque. Think about torque. If you apply force in the middle of the bridge, it's going to apply torque, which would cause the bridge or the actual member to bend, focus it, to bend down like this, and it would want to snap, and the bridge would want to do that. Well, the ends of this, they rotate the other way, or they apply a moment in the other direction. So when these are fixed in the wall, you draw moments in the opposite direction that torque will cause it to rotate. So if you're not sure what I'm saying right now, maybe leave the bridges in half. You put a force here, which way would this half of the bridge go? Clockwise or counterclockwise? Not down or
clockwise.
Clockwise. It would rotate like this, right? If you apply force right here, snap the bridge, put a force, it would rotate like that, right? So look at the moment. Which way is it drawn? The other way. It's a reaction. A reaction is always opposite of the actual value itself. So the same thing occurs for the reaction forces at the end. These are fixed end moments, but because the bridge has a force acting down, there's actually a reaction force also at the end pulling back up at both ends. We call these R. So this is like RY1, RY2, and this is M1 and M2. I'm giving you, honestly, this is a preview of second year engineering mechanics of solids. This is where I kind of learned this stuff. But just an idea of where it's coming into play. Okay, it's really, I'm simplifying things obviously a little bit, but the concepts are really no more difficult than what I'm teaching you right now. Let's see. I have notes on here that I wrote for myself. Open fixed end moments. Oh, I know what I mean. Okay. See how like civils use tables a lot, whereas mechanicals always do all the real heavy math. Civils don't really go into a lot of this. They go right into the tables and do their stuff. They don't really do the calculus involved. So it doesn't matter either way, but I want you to see that these tables are used widely. So here, now look at the second scenario. How is the first and second scenario different? There's one difference. That's only.
So different location.
Yeah. The first scenario, P acted at the midpoint, didn't it? P was always at the midpoint. Now it's at some arbitrary location, A away from the first end, B away from the second end. But look at your formulas now. You need to really be looking up here, right? Because I don't think you see this in front of you. This document is not even on Moodle, is it?
No.
No, so you need to be looking up here. So this distance, B, is a certain value from the end. It's used in the formula on this end, but it's not squared. Where on this end, it is squared. So these are different formulas. Okay, keep that in mind. I'm going to give you homework on this, so you're going to practice this stuff. It's not really hard. All you need to do is analyze the scenario and figure out which table you're going to use or which formula you're going to use. How about this third one, obviously? What's the difference there? What's the difference here? Yeah, there's two forces or three sections of the bridge now because there's two forces acting. The one after that, three forces acting. You see what's happening, obviously? Until finally you have something where there are many forces, and we call that a distributed load. So imagine, this is hard to explain. I'll give you an example. You want to ask your question first?
I just asked if it was on the wall.
Yeah, I'll put this on the for sure. It's just not on there right now, but I'll make it visible in a minute. And it's fine that it's not because I'd rather look up. So a distributed load is something like this. Conan, do us a favor. Lay it out on the table.
Okay.
Take a look at that. You probably love this, right? It's a great test.
I love this.
Go ahead, lay it down. So Nick right now is acting as a distributed load on like 2/3 of the table. His weight is not acting in the middle, even though in diagrams you always draw it from the middle down, right? Whenever we do free-body diagrams, the weight is from the middle. So I would say that there's a heavy distributed load in this area, in the middle of your body, a little bit lighter here, and very little distributed load here, whereas this end of the table does nothing. So a distributed load, is the idea that you're displacing a force over an area. Think back to physics last year. What was force over area defined as? Who remembers?
Mass.
No.
That's force over acceleration. What is it?
That's pressure.
Pressure. Good. There you go. Pressure. So really, a distributed load is just pressure. That's all it is. The easiest thing to think about a distributed load. Have you ever been under a pool before? Underwater in a pool, and then like in-ground pool, not a regular pool, maybe not above ground. When you get to the bottom, you feel the pressure on your ears, right?
Yeah.
Well, really what's happening is the weight of the water is acting on the whole surface of the floor when you're not in it. It's applying a distributed load at all times. But it's in a state of equilibrium because the actual structure of the pool pushes back. And that's, if you remember Pascal's principle with the egg last year, tried to crush the egg. So this idea of a distributed load,
When he tried to crush the egg and then he crushed it and it got all weird.
And I never even did it for extra credit.
I'll go back and change your grade by .001 on GPA for last year.
Thank you.
Because that's probably what it gave you in the end.
Egg.
You have the video? Okay.
Oh yeah, I have to.
I got a couple of those saved actually. So. Not yours though. So a distributed load, the concept is that it's applied over a certain distance, usually the full length of the span of the bridge. A distributed load, an example, is the weight of the object itself. A bridge does not just act down the middle, right? The weight of an object really is not from a point in the middle. It's really over the whole surface of the whole material span. So a bridge pulls down at every location from its weight alone. The gravitational force, the weight of the bridge, is acting down at all locations really. So in physics last year, what did we do? We simplified things a lot. We said, you know what? The weight of the object is always drawn from the middle down. That's what we did last year. But that's not really the case. The weight of an object is distributed over the actual material surface span, whatever you want to call it. Okay, the geometrical size. The second one here, obviously the distributed load only acts on half the bridge. The next one, this is an interesting one. So what could you say about this one?
That's like how Nick was.
Yeah, that's great. It's similar to how Nick was. Yeah, the distributed load is not consistent throughout. It's a function of distance. In this case, a linear function. So on this end of the bridge, is there more or less? More. At this end, there's no distributed load at all. Okay, and look at your formula at the bottom. What do you notice the difference in the formulas? They were dividing by 20 and 30. So this number will be smaller, won't it?
Yeah.
Because of what's happening, obviously. Yeah, there's less moment, there's less force on this end of the bridge over here. And then a distributed load that has a peak in the middle. Look at the forces at the end, the fixed end moments rather at the end. What are they? They're the same, right? Why are they the same? Caroline, you answered this before. Why are these the same? Yeah, because of symmetry. And then finally, this one has to do, and I'll explain this. This has to do with the deflection in the bridge. If the bridge undergoes natural deflection, you can determine the moment based on what's called E, the modulus. E is like K. Remember K last year was the spring stiffness, the rigidity? E is the modulus of elasticity. It's how much a structure can bend easily. I is called the moment of inertia. Moment of inertia is its tendency to want to rotate or not want to rotate, like mass. Mass was the mass, the tendency to stay at rest or move, inertia. This is called moment of inertia. We're not going to do stuff with this in this class. So you don't have to worry too much about it, but I want you to be aware.
Both of those are even on both sides, right?
Yeah, the deflection itself is naturally occurring in the bridge. It's not something that there's a force applied to it.
Yeah.
But again, don't focus on that one as much. On the right-hand side over here, what's the difference between the left? They're all the same in setup, but there's something that's different. Can you see it, Ant? What do you see?
B is not parallel.
Yeah, well, that's not the word, but yeah, it's not perpendicular to the structure. It's not what's called cantilevered. Remember, these are cantilevered. So this bridge or this structure, this beam, it's really called a beam, is embedded into the wall on both sides. Here, it's not. It's just resting on the surface. When something rests on a surface, it cannot provide what's called a moment. It cannot provide a torque. So you'll notice there's no fixed end moments on any of these. See the difference? All of the moment has to be prevented rotation from here. What would this apply? A force back up. So if there's a force acting down, this will apply force back up. But this is called a pin or a roller. A roller is the term usually used. A roller support. It simply means that it's not embedded into a wall, so it can't prevent rotation. Okay? So for example, if this were to want to rotate, this would not stop it from rotating. This is what's stopping it from rotating. Yeah, or like a rolling pin. You'd roll dough and knead dough with. Same idea. It's a roller. It's a cylindrical object. So they're all the same setup, just different answers because you don't have support on the right-hand side in any of these structures. So the left-hand side moment, notice, is greater than what it was over here. The moment here, okay, they're all different on each side. These are the same diagrams, except what else do you see in the diagram? It's not obvious, actually. I can't remember. Yeah, a lot of numbers, I know. So let me give you a little idea of this first one. Let's look at the first one over here. So this one, if you recall, the moment was PL over 8 on both sides. This is the reaction force. That's an arrow pointing up. That's a reaction force itself. We're going to continue this tomorrow. We'll pick up with this slide. Tonight, actually I won't give you homework tonight. I'll give you homework tomorrow night though. So if you have other classwork to do, please get it done tonight. I'm going to give you homework on this. It's going to take you a little while. But that will be tomorrow night. Okay? Yes?
What if there was an additional, let's say, X force that wasn't,
Horizontal?
that wasn't symmetrical with P, but it wasn't right down the middle, so how would you would you do the same problem over again with different distances?
When we get to truss structures, we're going to do that actually. I'm going to go through all the math behind it. But if you're talking about a force horizontally, right? You said X. Oh, some given other force?
Yeah.
Okay. If there are more than 2 or more than 3, you have to do what's called the sum of the torques and the sum of the forces. And we're going to do that. We will, with trusses. But for now, these are the values that you would get. But if we sum them together and did all the equations of motion, this is what you would actually end up with. So it would change it for sure.
But how would the distances change?
Where is this other force, though?
Like on the other side, but not symmetrical with P.
Yeah, so you would need like C and D. Like that. And it would be called what's superposition. You'd have to, you'd have to combine the two. It's a little bit tricky. It's not impossible, but it would definitely change the answer for sure. The easy way to derive it, to show where these come from, to show where these values here, not these are using calculus, to show where these values come from, is to do sum of the forces and sum of the torques. Do you remember sum of the forces equals MA? Sum of the torques is a little bit different. Sum of the torques for a bridge should equal 0 technically, so it's not rotating. Instead of MA, it's really what's called I alpha. It's rotational inertia. It's a topic that Mr. Donachek covers in AP Physics. We don't cover it junior year in either class. But I is like mass, and alpha is like A, acceleration. It has to do with rotational inertia. Rotational stuff is a lot trickier than linear stuff. That's why it's not really covered in junior physics ever. But in AP Physics, he covers that topic. But we're going to do rotational stuff when we get to trusses. So I'm going to show you that. And if you recall from last year, remember the lab I did last year where I gave you a piece of wood and you had to hang weights at different locations to get it to balance? That's what we're going to be doing to derive this. Okay? We're going to use that to do that. It's logical. It has to do with the balance between like a seesaw. Okay, so what I wanted you guys to see was that in these diagrams at the bottom, not only are you given the reaction moments, but you're also given the reaction forces. So you should be able to use these two diagrams. The next one, don't worry about. That's if you have a torque in the middle of the bridge. Not a force, but a torque, which you actually can have if there's something that needs to be rotated. And then this, again, is a deflection one. So don't worry about these last two. I really want you to focus on these two, and then over here on these two. So these two are similar to, again, the ones that we had on the left. Let me point back. So if you look, this one is this one up here. This one right here is coming from here. And this one right here is really the same thing as this one right here, just reversed, right? Okay, these, where they have a free end, see these ends are all free, we talked about this yesterday. There's no diagrams down here for these ones. Okay, the forces in these diagrams are all P over 2, this thing. The force is QL over 2, QL over 4, 7 QL over 20. Those are all forces, but those are all referring to diagrams from here. So these diagrams with forces are all shown right here. These ones, there's no force diagram given for that one. Okay, this is actually a lot easier to determine. Now, let me explain a little bit more to you real quick what the nature of this arrangement is, what this is going on here. It's called a roller. I talked about it yesterday real quick. And somebody talked about like hair rollers, I think. Somebody said hair rollers. Yeah, it was you, Caroline? Hair rollers. So imagine that you have this bridge and it's sitting on this support. But on this end, it's actually embedded in the material. So one end of the bridge is actually embedded into the desk. The other end of the bridge is just resting on here. Right? It's just resting. What would happen is this desk would prevent it from moving down. It would stop vertical motion. But it would not prevent it from rotating. It could rotate on its own, but it wouldn't be able to slide down. So this cannot provide a reaction moment, whereas this one can. This one, again, is fixed in the wall, so it's like a diving board. Think about a diving board, okay? You go to the end of the diving board, you jump on the end. Does the beginning of the diving board move at all? You better not, right? Or else it's going to flip over and hit you in the head. What moves? The part you're jumping on, right? When you jump on the end of the diving board, it bounces up and down, it fluctuates up and down. This end, though, is not moving. It's not able to rotate. That's this end right here of the diving board. Okay? So this prevents rotation, whereas over this end, this thing only prevents you from moving down. It's like a surface. It's like a normal force. The bridge is sitting on a ledge. Why don't I have to worry about it moving up? Because what pulls down? Gravity. Gravity pulls down. So this bridge is not going to suddenly just lift off the ground and start floating above the ground. It's naturally going to push down. So this roller support prevents vertical motion, specifically in the negative direction. Again, it prevents the end of the diving board from actually bending. If you jumped on a diving board, it would sit there and bend, right? If you did it with this bridge, it wouldn't, because it's being supported at the end. If you jump in the middle of the bridge, what might happen though? Yeah, it could bow out, or no. It could, what's that called? When
Wiggle.
It's a good word for it. It could vibrate. It could fluctuate. Its middle could deviate. Deviate's the word I'm looking for. Okay, so the bridge is normally like this. You put enough force in the middle, it could bend a little bit. And we're going to talk about tension and compression and these forces as well, and that will help us understand this too. Now, I'm going to talk about one last thing, but I want to show you a diagram, and this is what we were just talking about, these supports. We did the roller already, and we did anchored. That's what we just did, anchored and roller. We haven't done a pin joint or what's called a thrust bearing. So to describe these, I'm going to show you a diagram first. So look on Moodle, go back to documents and handouts, please. There's another figure there that says like reactions, I think it's called, or something.
Yeah.
Yes, open that one, please.
Can't, yeah, it's copyrighted.
It's not copyrighted.
Fine Brothers. Teens React.
It's from my Villanova days, right?
Teens react.
Teens React.
Have you seen those YouTube videos where it's like teens or like old people react to like Slender Man or something like that?
Like viral videos.
No idea.
Next week.
Well, you haven't seen SpongeBob, so.
I'm not a. I do like YouTube though, but I'm not a huge YouTuber. I mean, relatively speaking, yeah. So we're going to take a look at several arrangements, and I want you to think about free body diagrams to understand these. You're going to see, this was my professor, by the way, back in 2005. I was a sophomore. So this is Run Gun. His name was Run Gun, Robin Nathan. And his joke, he was the nicest guy ever. He was one of my favorite, best teachers I ever had. But he was very corny. And he started the year by saying, my name is Run Gun, but I don't run guns, so don't ask me to buy guns. That's what we started the year off. And we were all just like this. We're software engineers. And we're like, what is this guy talking about? Who runs a gun industry? But his name was Run Gun. He thought it was like kind of funny. It was like a play on words. One of the best teachers I ever had. Like one of the best, but the worst introductory joke I've ever heard.
Yeah, I have a crazy.
I'm still in contact with him all the time, actually.
What did he say?
He said I have a really crazy physics teacher too.
Oh.
It wasn't a physics teacher though. This was he was a teacher for 3 of my classes actually. He was awesome. Anyway,
Did you go to Villanova?
so
I already said that. Nobody heard.
so the force acting on a system that's just in contact without friction at all would be the normal force, right? And we can see that in the first one here. That's the normal force pushing back up on your chair. Now, if there's friction, obviously, friction would also push against whatever the motion would be. And say you sat in the chair, it would want to slide that way. So the friction force would end up pulling back this way. So we have to consider the fact that we have other forces also. The second diagram is a cable rope system. So a cantilevered beam coming out of the wall that's also suspended with some sort of a cable. And this is really the basic primary idea of a suspension bridge. Think about it in your mind. A ton of cables is a suspension bridge. That's literally what that is. Take one of those cables, and that's what you have here. Now, a cable pulls back against the weight pulling down, so that's the force acting on it there. If you have a spring instead, depending upon what's happening, if this were a diving board or something that could vibrate, if it's vibrating up, it compresses the spring, so the spring pushes back. If it's pulling down, it stretches the spring, so the spring pulls back. So depending upon which way the fluctuation is of the board, the spring can either pull or push, depending upon if the compression or tension. Yeah.
So you know how like on the professional bridge, like the cords are actually like not coiled, but it's like braided.
They're woven, yeah, they're all woven
Does
together.
that have a spring-like quality?
Yep, that's exactly what it is. It would have a K value, exactly. Remember from last year? So those are just fishing line. And fishing line, though, is also braided, actually. So there are fibers in there that are all woven together. That's literally what you have in a suspension bridge. The smallest cables are like this small. And then those are all braided. And then several of those are then braided together until the cables on bridges are like literally like this much in diameter. They're huge. Okay, it's like braided, and then those are braided within others that are braided. The reason for that is it increases the tension strength in the actual cable. Yeah. The tensile strength is the word. See, remember how I told you I was like kind of jumping ahead to this topic when I usually cover it at the end of the year? So we haven't even talked about compression, tension, all that stuff. So just bear with me for a little while, but I'm going to try and get to that. I'm just trying to cover enough material so that when we do work on this project, you're a little bit prepared for it. Now, this is normal contact with friction, but with 3-dimensional friction. So take a look at it. Fz is the normal force. Fy and Fx are just the friction forces. So on your chair, when you sit on your chair right now, as soon as you sit on it, besides the fact that it has members, cross members here, you see on the bottom of these chairs? Oh, it's very light. The bottom of these chairs here, okay, you have these cross members. These cross members are preventing these legs from going out, from going like this, right? From separating. It's a stable system. If this was not here and you were heavy enough, technically it could separate, right? Now, if you didn't have that cross member, you would have to consider the fact that the bottom of the chair is preventing it from sliding because of friction in two directions, in the X and the Y direction. Not in the Z direction, because the Z direction is up and down, and FZ would be the normal force. So this is pushing back up against the chair. Here's the chair leg right here. Friction is pushing back this way. Friction is preventing it from moving left to right, front to back, and the normal force is preventing it from moving up and down. So we have to consider the fact that last year in physics everything was only 2 dimensions, right? But really it's 3-dimensional. Everything's really 3-dimensional. Now, a system that is not at rest being supported, but it's actually fixed at the bottom, prevents any sort of motion at all. So in this case, this object technically, it could rotate. So here, let's say that this at the end right here is sitting here. This object could rotate freely, right? Maybe it doesn't move down because the desk pushes back up. It doesn't move left to right because of friction, but it could rotate like this. As soon as we fix it, literally, like take this object, drill a hole in the table, Miles, drill a hole in the table, take this object, take the object and slide it into the hole in the table. Now, it has no degrees of freedom of motion. So not only can it not slide left to right or front and back or up and down, it can no longer rotate at all. So that's the difference in these two diagrams. This is fixed. Think about your arm. Your arm is a socket joint, right? It's able to rotate easily. I can't, my arm's terrible shape. That's like this up here, a ball and socket. Whereas here, it's not the same thing at all. This is a fixed support. So it is not able to rotate. So see these MX, MZ, and MY? Those are, remember the FEMs in the last diagram, the reaction moments, preventing it from rotating the beam? That's the same thing. When you draw a double arrow at the end, it means that it's a reaction moment, not a reaction force. So these are forces preventing it from sliding left to right, sliding front to back, moving up and down. Here, well this one, it cannot rotate at all. So it's not able to rotate about this axis, or about this axis. I need you to look up, please. Come on. I'm showing you with the diagram, right? So MZ means it cannot rotate about this axis. This MY means it cannot rotate about that axis. MX means it cannot rotate about that axis. So if it can't rotate this way, and it can't rotate this way, and it can't rotate this way, it is fixed. Okay? A fixed support means it cannot rotate in any direction. 1, 2, 3. None of those rotations are allowed. And it cannot slide in any direction either. Does that make sense what I'm saying? Okay, these little indicators are showing that there's no rotation allowed. Those are reaction moments.
Do you like your Apple Pencil more than a stylus?
I do. It's much, much better.
Really?
I would never pay for it though. I didn't buy it.
Can I have it?
No.
Can you order one and be like,
No.
for my teacher money, please give...
Mr. Richard gave it to like 5 or 6 of us to try out to see if they're worth it. If it's worth $100, my answer is no. If they want to buy it, and is it better than the originals? Absolutely yes, it is. But it's not worth $100. I couldn't believe it. You know these cost $100?
Yeah.
It's a rip. It's insane. It's such a ripoff.
It's just a stylus, right?
It's really just a stylus, but it senses if you press harder or lighter, so the line is thicker. It like recharges with this. And what's cool with Notability is that if you use your finger while it's on pencil, it moves the page. So that's kind of cool. So when you have the stylus activated it's through Bluetooth. When it's activated and you start writing with the stylus, if your hand touches, it doesn't show a line. Your hand acts as like the grab tool.
It's really only for like
Artists. Exactly. And he gave us a survey, and that was my response. Said if I were an art teacher, I'd be like, yeah, this is great to have. But any other class, honestly, no, it's not. Anyway, look at a hinge. Look at a hinge. So think about a hinge, and you can do this if I show you real quick. Actually, this is a double hinge. So this is the second. See the second diagram with the double hinge? That's what we're looking at with this. Take a look at this from last year. So the hinge allows me to rotate this way, right? See how it allows me to rotate this way?
Yeah.
So where's it rotating about? Where's the axis of rotation?
At the
Point to
bottom.
it. Where is it? Yeah, at the bottom, down here. Here's where it rotates about, so double hinge. Now, that rotation is allowed this way, right? So if you were to think about this as the axis, the ruler is the axis of rotation. Is that clear what I'm saying? So you would not put MZ there because it is allowed to rotate. So look at the hinge in the first diagram. You don't see MZ along the hinge, do you? You don't see any moment prevention along the hinge, along the direction, because it's allowed to rotate. That's what a hinge is for. It's made to rotate specifically. But can this thing move up and down?
No.
Can it move left to right actually? Like physically move, not rotate, move. Can it slide this way? So all the forces are prevented, aren't they? So X, Fy, and Fc are in the diagram, but M, whatever that direction would be in this case, is not given a diagram. So no force is prevented, or no force is allowed this way, or this way actually. Okay, it's not allowed in this direction either. It's not actually necessary to even show it in this direction because this is fixed. Okay, because it's fixed. But I personally, let me explain why it's not shown. It's not needed. As soon as you have two other forces there in those two moments, it's actually assumed that it cannot move this way either. So this Fy right here is also really there, but you don't even have to draw it there because of the fact that it's not able to move in those other directions. So think about the hinge. Here's the hinge, right? Lift it up like this. Stay with me, right? See how it's lifting? Can it rotate this way?
No.
Because the MZ is there. Can it rotate this way? No. And you can see that with the diagram, with the actual apparatus here. If I were to lift this up, yeah, clearly it's rotating about its rotational axis, but I can't rotate it this way, right? That was that one, and I can't rotate it,
Like push on the,
yeah, like this, the other directions pretty much, the other two rotational directions. But I can rotate it only about that one axis. That's what a hinge is made for. So here's a hinge with, this is really what we got over there. I had two hinges on the actual system itself, so this is the diagram over there. Now, in this diagram, there's no moments shown in the diagram at all. The reason they're not shown is because as soon as you have two forces fixed in these directions, it automatically means that it cannot rotate in those other directions. So it's like, remember how you would be given a physics problem and sometimes you were given a little extra information? You didn't really use it in the problem? It's extraneous. You don't need to show that because of the fact that these are fixed in both spots. If it's fixed here and here, how is it possible to rotate? It can't. When it's only fixed here though, you need to show that it can't rotate with the actual symbol. Okay, but if you fix something, think about it. If I drill a hole in my iPad, I wouldn't do it right now, here, and I put a screw through it right here, it can rotate, can it? Look at that, it's rotating about the axis. Now, Nick, I drilled two holes in here. Now can it rotate?
No.
No. So because we have these two hinges here at these locations, it cannot rotate in those directions automatically. So having two forces prevents this rotation. Having two forces prevents this rotation. But it still can rotate this way. Okay? You don't have to have this stuff memorized, but you need to understand physically what's happening. Okay? It's going to be useful in the next stuff we're going to do. So here's the ball and socket. Actually, it's perfect timing. The ball and socket, that was what we were talking about before with your arm. So your arm is able to rotate in any direction. Up and down, front and back, and then like this also. So all rotations are allowed for a ball socket joint. Is that clear? Now, obviously you have ligaments which prevent you to do what? Go too far, right? Yeah. Can't go beyond this, or you can't go beyond right here because your body's restrictions. But this, a ball socket joint like this, can literally be rotated all the way around. It can be rotated like this. It's pretty much like a roller bear or a bearing at the bottom, a ball bearing that enables it to freely rotate. What else? A single journal bearing. All right. So look at the system here. Don't even look at the diagram here. Look at the system. Which way do you think this is able to rotate? Can it rotate like this, you think? No, it looks like it's locked in there, right? Can it rotate like this? Which way can it rotate though? About its axis. See how I'm turning it? That's what that's made for. So it can rotate this way. So notice there's no moment along this line. There's no moment preventing it from rotating this way. But it is prevented from rotating up and down. Okay, it cannot do this and it cannot do this. Okay, this one here, this rotation, is prevented by this one. This rotation like that is along that axis. It's hard to visualize, so I'm trying to show you with these diagrams. What else? It cannot move up and down like this, right? Look at the system. It can't move like this, so the force is prevented, Fz. It can't move like this, right? It cannot come out of the page, so the force is prevented like this. But if I tried and I took a hammer and hit the side of it, what could it probably do? It could pop right out, right? So notice there's no force along the axis either. So along the axis, there's no moment because it can rotate about the axis and it can slide back and forth about the axis. If you wanted to prevent it to slide back and forth, that's called a thrust bearing. I think that's actually the next one. Let's see. Yeah, the bottom right here. Okay, so take a look at this one. Same setup. Do you see this? Literally the same setup as the last one, except it cannot rotate, it cannot slide this way. There's a little diameter of this small guy that's preventing it from moving. So this is called a journal bearing. Same exact thing here, but it cannot slide this way. Okay, it stops a mechanism from sliding out of the socket that it's in. And then this is a system of two of those, right? Okay, a system of two of these. So again, what can this one do? It can rotate this way, and it can slide back and forth this way. But if I have those forces alone, it tells me, well, I can't rotate this way, because again, figure it out, visualize, fix both of them here. If it's fixed in one spot, maybe it can rotate, we don't really know, but in the previous diagram we saw it couldn't because it was a collar. As soon as it's fixed in two spots, it's assumed it can't rotate. You know it cannot rotate this way, so you don't have to show those moments in this diagram. Okay, it's similar to the last one in that sense. All right. Do I want to keep going? Let me see if I want to keep going with this. No, I'm going to skip this slide for now. I want to really point out stuff that I want to go through, so let me see if I want to do this or not. No. All right, so this last one here, number 5 at the bottom, is what we've been talking about all along. This is the last thing I want to go over for this topic. When an object is cantilevered or fixed into a wall, this is what's happening. This actual system, you could draw it with a weld, see they put weld there, or you could technically extend this into the wall to show that it's actually embedded in the wall. If an object is embedded into a wall or into a support, it cannot rotate freely this way. The end of it, yeah, sure, that can fluctuate, but this end cannot move. It's literally fixed. And if you've tried this with the diving board, jump on one end, the other end should not move at all. Okay, it should be fixed in. So this should be fixed, so that's why you see this moment Z. And the moment Z right there. But if I had something like this, let me just differentiate this a little, or show you a little difference. This is called a pin joint. There's the member right there. What this tells me is that this object cannot move up and down, it cannot move back and forth, it cannot move like this, but it's allowed to rotate. It's allowed to rotate. It's similar to a hinge. So when I talk about pin joints, I want you to think about a hinge. A hinge allows for it to rotate, so this thing can rotate like this, back and forth. So if I were to draw the free body diagram of this, I would have prevented motion this way, prevented motion this way, prevented motion out of the board also, but there's nothing preventing any sort of rotation. So instead of having MZ there's nothing there for preventing rotation. See what I'm saying by this? Okay, do you see how these are different things? This is fixed in a wall. It literally cannot be moved. Imagine my arm is stuck here. Yeah, I can do this with my hand, but can this move at all? No. But now, this is free. It's not a pin now. Now, it can rotate nice and easily. That's the second one here. Okay? All right. Let's stop with this.